Good morning, everyone. My name is Diane Tigeser, and I'm the Senior Advisor, External Relations for the Global CCS Institute. On behalf of the Institute, welcome to our webinar, Overview of Current Directions in Carbon Capture R&D. Our presenter this morning is Ron Munson, the Institute's Principal Manager of Carbon Capture. Ron was formerly a Senior Engineer contracting to the National Energy Technology Laboratory in the U.S. Department of Energy. At NETL, Ron supported greenhouse gas emissions mitigation research, development and demonstration programs, including carbon capture and advanced combustion systems. In addition, Ron supported the DOE programs all along the commercialization pathway, from process concept through demonstration. Ron holds a Bachelor of Science and Master of Science in Chemical Engineering from Brigham Young University. Welcome, Ron. All webinar attendees are welcome to submit questions throughout the presentation through the Questions tab on the GoToWebinar control panel on your screen. Questions will be moderated and posed at the end of the session. Please be aware that we may not be able to get to all your questions today, but we will try to answer as many as time allows. Joining us for the question and answer period are Tony Zhang and Guido Magneschi, the Institute's Senior Advisors for Carbon Capture. Tony is based in Melbourne and Guido is based in Brussels. And now Ron will begin his presentation.
Thanks, Diane. And thanks to all of those who have joined us here today. I wanted to acknowledge the contributions of my colleagues at the Institute, Guido Magneschi and Tony Zhang, who helped put together this presentation and who will be available to answer questions at the end, as Diane mentioned it. I just wanted to go over give an overview of the presentation. First of all, I want to talk a little bit about some background information. Then I'll touch briefly on first-generation capture technologies, which we'll define here as technologies that are in use right now. Then we'll move into second-generation technologies. These are technologies that are or soon will be tested at pilot scale and are targeting reductions in cost. Finally, I'll talk a little bit about transformational or third-generation technologies that are at earlier stages of development but show promise for significant cost and performance improvements. So the information that is in the next couple of slides is familiar, but it helps to frame the discussion. All the projections that are out there show increases in global fossil fuel use over the coming decades. So if you look at the figure up here, you can see that fossil fuel use is going to be increasing over time. There's a lot being used now, and there will continue to be a lot of fossil fuel use as we move forward over the next few decades. We also have projections that tell us that if we continue to emit greenhouse gases into the atmosphere, we'll see significant impacts on the climate. The Intergovernmental Panel on Climate Change, or IPCC, has told us that if we want to avoid the most serious impacts of climate change, we need to limit the increase in global average temperature to 2 degrees C. That corresponds to a concentration of CO2 in the atmosphere of about 450 ppm. So how are we going to do that? Well, there's not just one approach that will allow us to meet our greenhouse gas emissions goals. We need to use a whole portfolio of measures to decrease atmospheric carbon emissions. This diagram shows the contributions of several of these measures in reducing emissions. The International Energy Agency has said that CCS will be needed to account for about 13 to 14% of those emission reductions over time. In addition, the IPCC conducted analyses that looked at the impact of eliminating different greenhouse gas mitigation measures. So using this approach, they ran several different model scenarios to determine how many could still achieve the 2 degrees C goal, assuming that some of the mitigation options were removed as possibilities. And what they found was that if they removed nuclear, solar, wind, and bioenergy, most of the models could still achieve the goals. And the added costs associated with meeting the goals were relatively small for nuclear, solar, and wind. They were a little bit higher for bioenergy. However, if CCS is removed, most of the models were not able to achieve the 450 ppm goal, and the costs of meeting the goal increased by 138%. So this just shows that CCS is a critical component in decreasing the costs associated with meeting greenhouse gas emissions goals. So where are we now in terms of CCS development and deployment? If we look at what has been done up to this point, what we see a couple of interesting things. First of all, most of the sectors, most of the large-scale projects have been in sectors where separation of CO2 from gas streams is really just a normal part of doing business. And this graphic shows that. So we've seen a lot of projects associated with natural gas processing, fertilizer production, and syngas production. The one exception to that is the Boundary Dam project, and I'll be talking a little bit more about that in later on in the presentation. So if we look at over the next couple of years, we see several additional large-scale projects that are projected to come online. In fact, they're projecting that 8 will come online in 2015 and 2016, and that'll represent a more than 50% increase in operating projects globally. If we look out farther in time, what we see is that there are many more projects that are projected to go forward in the power generation sector, but also important projects that will be moving forward in other sectors such as cement and steel production as well. In the gas stream that's being treated, you can either use a chemical absorption approach or a physical absorption approach. Chemical absorption involves the formation of actual chemical bonds between the gas and the solvent. They're attractive in that they have fairly fast kinetics. Faster the kinetics of uptake, then the smaller the reactors can be. And so, that approach is useful for low pressure operations, and so low concentrations of CO2 in the gas that's being treated. And so, for instance, post-combustion capture for power generation is typically looking at chemical absorption type of technologies. But a significant issue associated with that is that it requires a lot of energy to regenerate the solvent and reverse the chemical reaction. And I'll talk a little bit more about that as I move forward. The other type of absorption technology that is being used right now is physical absorption. And so in physical absorption, the gas and the solvent form fairly weak physical bonds. And that's nice because it doesn't require heat necessarily to regenerate the solvent, but instead uses a kind of a pressure swing to regenerate the solvent. And so it's nice for higher concentration gas streams, such as those associated with pre-combustion capture, or in a lot of cases, natural gas sweetening. And so, there's some distinct advantages to using solvent absorption technologies. And one of those advantages is that it's been around for a long time, and people really understand how it works and have experience using it. It allows for good heat integration and good heat management, and can handle, for chemical absorbents, can handle low partial pressure CO2 streams. But it does have challenges, and those include the fact that a lot of times the solvents used, the chemical solutions used, have to be fairly dilute. And so you've got an active solvent that has to be diluted typically in water. And so for instance, for amine-based capture, the concentration of the amine in the solution is typically on the order of 30%, maybe as much as 40%. And it has to be that low in order to avoid problems with viscosity and with corrosion. And that then leads to other challenges associated with using the absorption-based technologies. The Boundary Dam project that I touched on previously is the first project in the power generation sector where capture is being demonstrated at scale. Boundary Dam is a multiple unit power station that burns lignite coal, and previously, prior to this particular project, all of the coal, or all of the use, was unscrubbed, so they didn't have any sulfur mitigation on the plant up to the point of this particular project. And so the way that this system works in the picture, that is just the capture plant. The actual power plant would be off to the left in the picture. And so if you take a look at in the picture, kind of on the left-hand side, you have two reactors that have kind of triangular tops there. The first one is the sulfur removal reactor. And so the flue gas comes from the power plant, goes through the sulfur removal reactor to bring the sulfur concentrations down to appropriate levels so that the solvent can handle that. And then the gas is then moved into this larger reactor that has the steam coming out of the top, and that's where the CO2 is separated from the flue gas. That separated CO2 is then, or the solvent with the separated CO2 is then piped over to this kind of silver reactor sticking up above the top of the building there, and that's the stripping unit. And there it is, the CO2 and the solvent are separated from one another, and the CO2 is then moved to a compression system in the building where it's compressed, treated, and sent on for EOR operations in a nearby oil field. And so one of the things that I wanted to note here and point out is that these systems, these absorption-based systems, are large systems. And if you'll notice, just below the Sask Power sign on the building there, you can see a couple of cars parked in front of the building. And so that gives you some idea of the scale of these types of systems. And that's important in areas that I'll talk about as we move forward a little bit. So, capture systems are in place, but there are still barriers to deployment. And one of those barriers is the energy penalty. And what that means is that some of the energy that would normally be used in a power system, for instance, to help produce electricity, instead has to be used to drive the capture system. And so that can be in the form of steam or electricity. And what that does is that it degrades the amount of power that is generated by the facility by 20 to 30%. Another issue is the cost. And so, putting in one of these systems can have a significant increase in the cost of electricity. And that's another factor that needs to be addressed through R&D in the future. Another issue is scaling up these systems. Like I said, they're very large. The unit that is being treated at Boundary Dam is about 160 megawatts, and it produces, or it captures about 3,000 tons per day of CO2. 550 megawatt plant is going to produce a lot more CO2. Up until Boundary Dam, the larger capture units were on the order of in the hundreds of tons per day rather than the thousands. So if we take another look or a closer look at the energy penalty, and this is an example for post-combustion capture, what you see is that there are several different factors that play into the energy penalty. And so in the equation down at the bottom, it talks about three different heat energy terms. So you require heat for or energy for heating up the solvent, for breaking the chemical bond, and then for moving the separated CO2 out of the regeneration process. And then there are also energy penalties associated with the pumps and the fans and the blowers and that sort of thing that are required to operate the capture system. And then you also have a significant electrical energy input into the compression process. And so what that means is that in terms of increase in the cost of electricity associated with capture, over half of it comes from the energy penalty, whereas most of the rest comes from capital costs. And that's really just a, there are multiple factors that go into that, but the most significant of those is just the size of these systems. And so this is kind of a drawing of what the Boundary Dam system looks like. And so, one of the goals of R&D in helping to drive down costs is to reduce the size of the equipment. There's lots of concrete, lots of steel that goes into these large units, and so if the cost can be reduced, then that would be a significant benefit. And some of the technologies depicted here, I'm going to talk a little bit more about later. But again, if you can reduce the size of the equipment, then the cost goes down in a significant way. So the Department of Energy has an R&D program here in the US that is trying to reduce the cost of CCS. And so the targets that have been developed are for second generation and transformational technologies. And what they're trying to achieve is that for second generation technologies, they want to reduce the cost of electricity by 20% compared to the current costs associated with carbon capture. And they want to have those technologies ready for deployment or for demonstration starting around the 2020 time period. They're also funding the development R&D on transformational technologies. And those are technologies that have a more significant reduction in cost of electricity associated with them, and excuse me, and that will be ready in the 2030 timeframe. I was just at a presentation the week before last where they have indicated that their target is going to be a 30% cost reduction for the transformational technologies. Excuse me. So if you take a look at the different research and development areas that are being pursued, that's depicted in this figure that shows all the different areas. And so, one of the areas that's being pursued is CO2 conversion, or converting the CO2 into something else. Another area is CO2 condensation or desublimation, where you convert the CO2 into either a liquid or a solid and remove it from the capture system that way, or remove it from the flue gases that way. Another area that is being actively pursued is CO2 adsorption. So you expose the flue gas stream to a solid sorbent, and the CO2 interacts with that solid sorbent and is removed from the flue gas stream. Another area is CO2 absorption, and that is the solvent-based systems that we've talked about earlier. And some of those solvent-based systems are in use right now, but there are new solvent or new absorption-based systems that are under development as well to improve the performance. And then finally, the last general area is gas permeation or membrane-based systems. And there's a lot of work going on with membrane-based systems as well. Some of those systems have challenges associated with the low concentration of CO2 in flue gas from power production, but they're developing mechanisms to get around that. So if you take a closer look at one of the arms in that previous figure, what you see is that there are really three basic areas that are being pursued in terms of R&D in each of those categories. And those include materials, equipment, and processes. And so, for instance, for CO2 absorption, they're looking at materials that, for solid materials that do a better job of taking up CO2 and and require less energy. Different equipment configurations and processes, and I'll talk a little bit more about that. And then different ways of running these systems in more efficient ways. Again, going back to the DOE program, they currently have a whole series of projects that are undergoing testing at the pilot scale. So these are projects that have already been advanced beyond the laboratory scale and are now being tested at small pilot scale, which is typically in the 0.5 to 1 megawatt range. And then also looking forward to testing them at larger scale in the 10 to 25 megawatt range. And so if you look at projects that are ongoing right now in the DOE portfolio, what we see is that most of the pilot scale projects will be completed somewhere in the next 2 to 4 years. And then they'll be ready to move on to the large pilot scale. In the figure, the solid colors indicate projects that are underway and moving forward. The more opaque arrows show the timeline for developing these projects, so that they haven't been funded yet, but that's the time frame under which they would most likely move forward. And so what you see here is that for the most part, they are targeting large-scale demonstrations up to the 2020 timeframe, maybe just a little beyond, and then demonstrations following that in the 2020 to 2025, 2026 timeframe. The projects are in the similar areas that I talked about earlier. So we have solvent-based projects, sorbent-based projects, membrane-based projects, and then we also have some oxy-fired projects that are in the pilot phase as well. And so there are too many of them to talk about all of them, but I wanted to provide just a few examples of some projects that are moving forward in this pilot scale development effort. And so one of them is a project that is being conducted by the Newman Systems Group. This is a group in Colorado that is developing a contactor, a nozzle-based contactor that improves the contacting with the solvent stream with CO2, with the flue gas stream. And one of the significant advantages of that particular technology is that it allows for significant size reductions. And so this is a graphic depicting that. So again, looking at something the size of the Boundary Dam project, for an equivalent treatment for the equivalent treatment of an equivalent size gas stream, the Newman reactor would be much smaller, and again, drives down capital costs in a significant way. Another project that is ongoing is by Southern Company at Plant Berry. And here they're testing a Mitsubishi solvent at a 25 megawatt scale. And the project that specifically they're looking at here involves heat integration of both the power plant and the capture system to use heat that would normally be wasted. And so if they can use that heat, they can increase the efficiency of the overall process and thereby reduce costs. And so this is a project that is focused on process for the most part, but also some equipment in the specialized heat exchanger that they're using to facilitate this process. Another one that is solvent-based is a Linde, is being conducted by Linde at the National Carbon Capture Center in Alabama. And they are doing a 1 megawatt slipstream test that they've just recently increased their treatment volume a little bit, so they're at almost a 1.5 megawatt slipstream scale. And there they're testing a solvent that has improved characteristics in terms of uptake and regeneration. And so as part of that, they're projecting much lower electrical load. And they're doing this through capital cost reductions, smaller reactors. Only a 1 reactor train would be able to treat a 550 megawatt power plant, for instance. And so this is an area where they're really doing all 3 areas. They're doing advanced testing on an advanced solvent, so a material. They're doing some unusual process things and using some novel heat exchange approaches as well. Another project that is being conducted at pilot scale is by ADAES, and they are looking at an amine-based sorbent. They're doing their testing at Plant Miller, which is another Southern Company facility. And there they're testing a process that uses an advanced sorbent, an amine-based sorbent, and trying to see if by using that approach they can reduce costs. You know, sorbents have some inherent advantages, one of which is that you're not required to move around and heat all of the water associated with some of the solvent-based systems. And so because of that, you have some energy advantages. But there are challenges associated with that as well in terms of sorbent attrition and solids handling. And so they're working through some of those in their current project. Another sorbent-based project that is being pursued is a KEPCO project using a carbonate-based sorbent, and they're testing that at a 10 megawatt scale. And so there are some distinct advantages to the sorbent material that they're using, and then to the process that they're testing to try and make that technology operable for these power plant systems. MTR, which is Membrane Technology and Research, is also testing a 1 megawatt scale system at the National Carbon Capture System. And they are using an advanced membrane that they have developed. They call it a Polaris membrane. Over their development process at smaller scales, they have done a really good job at increasing the permeance and selectivity of their membrane materials so that they are applicable to these large-scale utility systems. They've also come up with a process that involves an air sweep that increases the goal of the process is to increase the concentration of the CO2 in the gas stream entering their main membrane, and so that way they increase the driving force and make the membrane more effective. And so they have been testing this 1 megawatt system for about a year, and they will be finishing up their testing at the NC3 in the next few months. Another process that is being pursued is calcium looping, and that's being pursued at a couple of different places in Europe and in Asia. This is a process that allows high capture and it's a relatively high temperature process, and so it's effective. But they're testing now to see if they can use the process, integrate the different components of the process in such a way that they can help increase the efficiency of the associated power generation facility. In terms of oxy-combustion, one of the projects that is ongoing right now is by Aerojet Rocketdyne. They're testing a 1 megawatt thermal unit. It will be tested at CanMet facilities in Canada. This is a system that uses pressurized operations to help increase the efficiency of the process. It allows for recovery of latent heat at more high quality, and has potential for decreasing costs associated with oxy-combustion in a significant way. And then the last second generation technology I wanted to talk about is an Alstom chemical looping technology, and they use limestone as their sorbent. Chemical looping is a process that is very different than most of the other processes that we've talked about, but it has significant potential in terms of cost reductions. It would use smaller equipment than is typically used in power generation, and also has the potential at least to result in significant reductions in CO2 capture costs. And so one of their projections indicates that it could achieve capture costs of under $30 per ton. In terms of transformational technologies, there's a lot of work going on, and most of this work is at the laboratory and bench scale, but it involves testing of technologies that can really have a significant influence on the costs associated with capture. So a little less than a year ago, there was a workshop that DOE held on transformational technologies, and they talked about some of these topics that are on the slide here. And so, there's a lot of computational work that is moving forward that will help design systems that are more robust and more effective at capture. And the hope is that can decrease some of the time that will need to be spent on experimentation. It'll be an effective guide for experimentation. And so, they were also looking at some of the experimental aspects, looking at advanced manufacturing that could then be used to create these capture systems in a more efficient way and decrease the costs associated with that. And so I wanted to talk a little bit about just a few specific projects here. One of the interesting ones that's being developed is by ATK, and they're using supersonic expansion to solidify the CO2 in the gas stream and then separate it out. And so they're currently testing at a 0.25 to 0.5 megawatt scale. It's got significant advantages in terms of operations, no moving parts, no chemical handling or to deal with, and the one of the most interesting parts of it is that the scale would be much smaller. And so if you take a look at the picture there, the larger unit is the pilot solving testing unit at the NC3, and an equivalent unit, a unit of this supersonic expansion technology that would treat an equivalent amount of gas is the one shown down at the very bottom of the picture. And so you can see it's a huge difference in the size of equipment that would be required. Another very interesting approach is one being developed by Fuel Cell Energy, where they use fuel cells to capture CO2 and produce power at the same time. And so that's a technology that is being tested and shows great promise. And so if they were, one of the things that they talk about is that if they were to capture carbon from a 550 megawatt power plant, they would generate an additional 400 megawatts of power associated with their process. And so it has real potential to have a significant impact on capture costs moving forward. And then another interesting area is looking at phase change solvents. And so GE Global Research is involved in a project there where they're looking at an aminosilicone solvent that was developed as part of a previous project. And this solvent, when it's exposed to CO2, forms a solid. And so GE is looking at a process to capture that solid and regenerate the liquid phase solvent after they drive off the CO2. And so there are a lot of real advantages there in terms of loading and thermal stability, and then being able to generate the separated CO2 at pressure, which would reduce compression costs. So just to summarize, we've covered a lot of different areas that are interesting in terms of the technologies being developed, but they all boil down to really three main areas that they're trying to pursue. And those include materials, processes, and equipment. And so in terms of materials, they're trying to develop higher performance solvents, sorbents, and membranes that have faster kinetics so that they can decrease the size of the reactors, lower stripping energies so that the energy penalty isn't quite as bad as it is now, or as high as it is now, and just increase the permeability and selectivity of membranes to drive down costs. So in terms of process improvements, they're looking at different ways to integrate heat and to move different processes into single reactors, for instance, and that would decrease the costs associated with building those capture units. And then in terms of equipment, they're looking at novel designs, so novel ways of contacting the solvent or the absorption medium and the capture medium, and doing it in a way that decreases the sizes of the reactors, and then also looking at advanced manufacturing techniques to make those reactors and that equipment smaller and easier and less expensive to produce. Okay, so with that, I'll turn it back over to Diane and answer any questions that people might have.
Thank you, Ron, for an excellent presentation. If any of you have questions, please submit your questions in English directly into the GoToWebinar control panel, and we'll try to get to as many of them as time will allow. Our first question is, are there any notably promising industrial CO2 capture technologies?
Yeah, that's a good question. And, a lot of the technologies that are being developed that may be power sector focused are applicable to industrial operations as well. So for instance, there are technologies, post-combustion capture technologies that would be applicable to the steel or cement industry. And so, you know, both in the power sector and in the industrial sector, each individual operation would have to take a good look at what their specific requirements are and needs are in order to pursue the most effective capture technique. But a lot of the techniques that I mentioned today, you know, that were kind of presented in the context of the power sector are equally applicable to the industrial sector.
Okay. Our next question is, you've talked about a number of technology approaches to reduce the energy penalty of carbon capture. While not asking you to pick favorites, in your view, which ones seem to show the most promise and why?
Well, again, it's you know, avoiding picking any favorites. There have been real significant advantages or demonstrated for some advanced solvents in terms of regeneration energy required. And so, you know, one of the biggest issues with the current aqueous-based solvents is the regeneration energy associated with all that water that you're carrying around. And so if you can somehow reduce that, that's a significant advantage. And so there are technologies, solvent-based technologies that are being developed that do that. And some of those use non-aqueous solutions. And those certainly have some promise in terms of reducing regeneration energy. And then just some of the process type of R&D that's being done also has potential for significant energy reductions. Tony, do you have any thoughts regarding some of the reduction in technologies and their impact on energy penalty?
Well, I quite agree with what you have just said, and I think for the different technology options, and quite often you need to find a proper trade-off. And for example, for solid sorbents, you always need to find out the best working capacity, but at the same time, you also want to improve the selectivity of the materials. And so I reckon it's at this stage, really every different technologies have shown their own strengths and weakness, but I think people are doing a lot of good work to improve and to try to reduce these energy penalties. Yeah.
Great. Okay, thank you.
Okay.
Any thoughts, Guido, that you'd like to add?
Yeah, I think that more or less all the new technologies of second and third generation are trying to achieve like a much larger energy savings in operation. Membranes are probably the one that offer the largest energy saving because they don't require heat for working, even though they require a large footprint. I think that when we talk about energy use from capture processes, one important aspect to consider is the waste heat utilization. And this is especially true for industrial facilities where some waste heat otherwise wasted can be used in capture technology. For instance, if you have low temperature solvents, they can reuse low temperature waste heat that is often available at industrial facilities. So this is also an aspect to consider when we are talking about the energy performance of this kind of systems.
And that's a good point. Process integration is a significant issue for reducing energy penalty. Okay.
Okay, our next question is, are the DOE energy targets arbitrary, targeted reductions in energy, or are they based on some background science and approach to ideal conditions? And therefore, how achievable are they?
There are a lot of things that have gone into those DOE targets, and at least the second generation target has been at that level for a few years now. And what they're seeing is that the different developers are working toward those targets, and they are making strides towards those second generation targets. And so I think that that there really is strong potential for getting to those targets. If you ask DOE, they will tell you that their targets are aggressive, and that they know that it's going to take a lot of work to meet those targets. But from the standpoint of the developers, at least, I think that putting that target out there for them has been a significant benefit in terms of knowing where they want to try and get to. And so, especially for those second generation targets, I think that there's some good basis for where they are. The transformational targets are out there even further, and they're going to be tougher to achieve, but they know that they're going to be tougher to achieve. And so that's why the development timeline is what it is in terms of trying to approach those more transformational targets out farther in time, in the 2030 timeframe.
Okay, our next question is, what is your view about the biphase solvent for CO2 post-combustion capture?
Again, I think there's potential for them, and some of that depends on what we're talking about. For the phase change solvents, so the ones that form solids, there are challenges associated with that type of a process that just go to moving the material around and dealing with the multiple phases, and that without question is challenging, but they offer some significant advantages in terms of energy that really warrant pursuit. And so I think that they definitely do have some potential.
Our next question is, several of the methods had challenges around solids handling. Are there any emerging technologies focusing on solids handling in other industries which could be applicable?
Yeah, I think that we really need to, in CCS, take advantage of solids handling understanding and knowledge that exists in other industries to a more significant extent than I think has been done so far. And so, the petrochemical industry, for instance, has a lot of experience with solids handling that I think could be applicable to carbon capture systems as well. So I think that there are areas that need to be pursued that I think the developers are heading in that direction. Guido, do you have any thoughts on that?
Yeah, to my experience, I think that when it comes to solid sorbents, the existing knowledge that is coming from other industry is already put in place as much as possible. So, yeah, I think in that respect, the problem that are faced by this kind of systems are different, and the question is maybe more how to achieve like the wanted efficiency of capturing CO2, or how to avoid the degradation of these solids during their use. And these are of course questions that are much more specific to capture CO2 capture system, and they are under investigation at this moment.
Okay. Our next question is, are we seeing any consistent trends in reducing the time from lab to commercialization?
I don't know if we can really claim consistent trends. I think that some of the work that's going on, some of the computational work that's going on, has the potential to reduce that time. And, you know, there are some specific instances where that you can cite where, you know, new sorbent materials have been developed that have benefited from some of these computational approaches that would have taken longer to develop using a purely experimental approach. I don't know that we're far enough along in the process yet to make any generalizations regarding consistent reductions in time. But that's the, you know, that's why those computational type of approaches are being pursued, is to try and reduce that development time. There's the Carbon Capture Simulation Initiative that is a DOE NETL initiative that is specifically targeted to do that. And, you know, they've been in existence now for, I think, about 4 or 5 years. And we're really just kind of seeing the beginnings of the benefits to the approach that they're pursuing. So I think there's potential there to see some interesting things coming in the next few years.
Okay. The next question is, what are the pros and cons of ionic liquids for CO2 capture?
Yeah, ionic liquids are an interesting class of compounds. You know, they one of the big advantages is that they don't carry with them the requirement of water, and so, you know, you reduce the energy associated with the water in aqueous phase solvents. And so they typically can have fairly high loading capacities, you know, depending on the makeup of the ionic liquid itself. It can have some fairly decent kinetics, which would decrease the size of absorption reactors. And so there are very attractive things about them. The challenges with ionic liquids, you know, one of the big challenges so far has been with viscosity. When they're exposed to CO2, you end up forming hydrogen bonds that basically just gum up the solvent and make it very difficult to move, make it very difficult to have good contacting with flue gas streams. And so that has been a significant challenge. You know, one of the things that they're pursuing with ionic liquids, non-aqueous phase solvents in general, is one of these computational approaches that I was talking about before, where they look at intramolecular versus intermolecular hydrogen bonding. And so if they can develop kind of these designer molecules that have more intramolecular hydrogen bonding, that has a significant impact in terms of reducing the viscosity. And if they can then experimentally produce those same type of compounds and they behave in the way that the simulations suggest, then that can be a real significant improvement in the performance of ionic liquids.
Okay. Unfortunately, we were not able to get through all of your questions in the allotted time. However, for any of you who still have questions, you may submit them to the Institute by emailing us at webinar@globalccsinstitute.com. This webinar has been recorded and will be made available on our website along with a copy of the presentation. This webinar is one of a series of expert webinars, and I hope that you found it valuable. On behalf of the Institute, a big thank you to our presenter, Ron Munson, and to our panelists, Tony Zhang and Guido Magneschi, for a most interesting and informative webinar. Lastly, as you leave this session today, it would be most appreciated if you would take the time to complete a very quick 3-question survey that we use to improve our webinar programs. Thank you all for your attendance. Goodbye.